Hello class, welcome to the channel and welcome to this playlist in which we are discussing different types of fault which takes place in power system. Initially we discussed about uh, symmetrical faults. After that we got a bit of glance of unsymmetrical faults. In previous videos, last few videos, we saw uh, positive, negative and zeroth sequence, and then we saw sequence impedance of my synchronous motor. So if you want to know more about it, please click on the link which is flashing on the top right hand side corner of your screen in the I button, because this lecture needs you to needs the understanding of those concepts in order to understand today's topic, which is sequence impedance of my transmission line. So we saw earlier that power system elements like synchronous machine or transformer and transmission line all are having some sequential impedances, and we have studied that sequential impedances in networks of synchronous machine in last lecture. So let's see the sequence impedance of my transmission line. And transmission line is going to be a little bit different because if you think about it, the transmission line is always transposed, right, to everything. So three-phase transmission line will be completely symmetrical because of this fully transposed quality of it. And because of that, what will happen, the per phase impedance which is offered by it will be independent of the phase sequence of the balanced set of currents. So the impedance which will be offered by your positive and negative sequence will be identical, will be same, but the zeroth sequence current will be different, right? How? So whenever the zero sequence current will flow in the transmission line, the current in the each phase will be identical and uh, in same phase, like magnitude wise it will be identical and it will be in the same phase. So phase angle and magnitude will be same. So that current will get divided in two parts. One part will carry majority of current and another part will carry small fraction amount of current. So this small fraction part of this currents will be current will return via ground, and the remaining first portion will return through the overhead ground wires. So these ground wires are grounded at several towers. If you have seen these ground wires or the towers, you will see that your ground wires are grounded at several towers. So so that the return current in ground wires will not be uniform. Like it can be uniform, but it not necessarily will be uniform all the times for the entire length of my line. So the flow of this zeroth sequence current through my transmission line or say ground wire and even your whole conductor, it will create a magnetic field pattern. Okay, ground wire or transmission line, whatever you say, or your conductor, it will create some magnetic field pattern, and this pattern will be different which was produced by your positive sequence and negative sequence. So because positive sequence and negative sequence will have identical, but it will be zeroth for zeroth sequence. So the zeroth sequence of impedance of my transmission line will also account for the ground impedance. So whenever we calculate zeroth sequence impedance, we have to calculate or we have to include the ground impedance as well. And usually the value of this zero sequence impedance for transmission line ranges from 2 to 3.5 times greater than your positive sequence impedance, right? Now let's come and see this figure. What is happening here? This figure is showing that I'm having a transmission line, three-phase transmission line, which is fully transposed, and it is carrying unbalanced currents, right? So it is having current, phase A is having current IA, phase B is having IB, phase C is having IC. All three lines are having identical self reactances of each line of their selves, and the reactance which is implying they are implying on each other is given by xm, and voltages on left hand side or sending end are given as va, vb, vc for each individual line, and on the receiving side are va dash, vb dash, and vc dash. And because we are grounding my tower at some distance, the sum of ia, ib, and ic will be equal to my in, which is the neutral line current, right? So this return path for in will be sufficiently well too much away from my transmission line, and because of that the mutual effect is normally ignored. But let's try to figure out the value of uh, sequence impedances of all three type of sequences. So for that, let's take kvl in this circuit. So when we apply kvl in this circuit, come here and tell me what will be the value of va minus va dash. So it will be equal to the multiplication of current with its reactance. But we are it is not as simple, because we are also having not only self reactance we are having, but we are also having mutual reactance. So mutual reactance will also come here in picture. So for current ia, its self reactance will be included in the calculation of impedance. For ib, mutual reactance will be included, and for ic, mutual reactance will be included, because we are calculating between va and va dash. So same ways, when we calculate for vb and vb dash here, you will include uh, whenever you're calculating for ib, you will include this excess, and for ia and ic, you will calculate you will include value of xm. So you can see it here, and same ways for ic, you are including excess for vc minus vc dash, and for ia and ib, you are including xm or mutual reactance. Now when we write it in a matrix form, it will look like this: va, vb, and vc minus va dash, vb dash, and vc dash will be equal to my reactance matrix into my current matrix, right? Diagonal values of reactance matrix will be the self reactance, and except for that, all the values will be mutual reactance. So you can represent your whole matrix via vp minus vp dash, which will be equal to x into ip. Now what we will do, we will multiply both of the side with a. And what is a? Remember your alpha operator, the matrix which included alpha operator, we called that matrix a. So we are basically multiplying with that matrix only. So after multiplying, we want to find the value of vs minus vs dash. So what we will do, we will simply send this a on the other side, so we will get a inverse. So in the previous class, we also discussed the value of a inverse, we derived it. So we are not deriving it again, we are taking it as it is, and we are taking the multiplication. We also know the value of x. This is basically the matrix x, right? Multiplied j inside of it, and then we have value of uh, a, and we have value of is. So after taking multiplication of all of them, what you will get, a inverse into a inverse x into a is equals to j xs minus xm, rest of the elements 0. So you will only get the diagonal elements. It will be and for positive and negative sequences, it will be, or for x11 and x12, it will be xs minus xm, xs minus xm, same. But for the zeroth sequence, it will be xs plus 2xm. So again it is showing us how the positive and negative sequences are holding same sequential impedance value. And when you take the final multiplication, when you multiply this matrix with your current matrix, you will get the final value of your vi minus vi dash, or v1 minus v1 dash, v2 minus v2 dash, v0 minus v0 dash. and you represent this xs minus xm with z1, this xs minus xm with z2, and xs plus x m into 2 is z0. And this z1, z2 and z3 are positive, negative and zero sequential impedance respectively, right? And what does this equation indicates to us? It tells us the equal positive and negative sequence impedances are present here. Z1 and Z2's value are equal. Second thing, the zero sequence impedance is larger than the positive or negative sequence impedance, because it is having xm two times, and also it is not getting subtracted, it is getting added here, right? So it is greater than the positive and negative sequence impedances, and there is no mutual coupling between the sequence network, right? As you can see, the sequence network will be independently represented from each other. So that was the sequence impedance for your transmission line. Now let's see the sequence impedance for my transformers. And as we know, the transformers are basically the static devices, so they will have the leakage impedance, and that leakage impedance will not change with change in phase sequence or balance applied voltage, because it is basically a static device. So the positive sequence series impedance of my transformer will be again equal to its leakage impedance, and same will go with the negative sequence impedance as well, right? But again, this time, one more time, the zeroth sequence impedance of transformer will be different, slightly different than both positive and negative sequences. And how will it be different? Let's see. So we know that transformers are having different types of connections, right? And zero sequence network will also have different types of connections. So we know, we by doing some observations, we learned that we can uh, take some different observations and consider them while calculating zeroth sequence impedance for my transformer. So what will be these observations? So first observation will be very obvious thing. Whenever we neglect the magnetizing current of my transformer, the primary would carry the current only if there is current flowing in the secondary side. If there is no current in the secondary side, the primary will not be able to carry any current either, which is very basic thing if you know about transformers. The second thing, zeroth sequence current can flow in the legs of a star connection, but only if a star point is grounded. If star point is not grounded, there will be no flow of zeroth sequence current, right? So grounded star point will provide necessary return path for your zero sequence current, and because of that it is required. And about delta connection, so there will be no zero sequence current flow in the lines connected to the delta connection, because there is no current path available for these currents. But the zero sequence current will be flowing in the legs of my delta, right? Because such currents are getting produced because of the presence of my zero sequence voltages in my delta connection, so there will be present there. Now let's try to see some of the types of transformer connections for, and what will happen with those topologies, and what will happen, what will be the zero sequence network for those topologies. So first let's consider the delta delta connection with one neutral grounded. As you can see here, the one neutral is grounded. So if there are two neutrals in delta delta, both of them are ungrounded, so there will be no flow of zero sequence current, and that is very basic. I don't even need to explain that. So the current will not be able to flow in the ground star, because initially I told in the second point of observations that we need a ground network for the flow of the zero sequence current. So if there is no zero sequence current, there is no if there is no ground plane, there is no zero sequence current. So the current will not be able to flow in the ground stars. So you can see the open circuit present here with H, and there is no connection of my my zero sequence impedance with reference bus whatsoever. The next point is the delta delta transformer, but this time we are grounding both of our neutrals. So what will happen in such case? So when both of the neutrals are grounded, the path for the flow of zero sequence current in the both of my windings will exist via two grounded neutrals, right? So because of that, the zero sequence network H, L, and will both be connected with each other, as you can see here, and the zero sequence impedance will be uh, present here, right? And still H and L will not connected with reference bus whatsoever. It will get connected eventually when we discuss about the delta, but let's move further and see what will happen to the when we are considering delta star transformation with my delta grounded. So the neutral of my sorry with my star grounded. So the neutral of my star side is you can say grounded, and because of that there will be presence of zero sequence current, so it will flow in the star because the path is available through the ground. But the balancing zero sequence current will only be can only be flow in the delta, but there is no current that can flow through the lines of connected delta, right? And because of that, what will happen, the zero sequence network will have a path from line H on the star side through zero sequence impedance of transformer to my reference bus. As you can see here, H is connected to my zero sequence impedance and to the reference bus, right? Reference bus of my transformer. But on the L side you can see there is an open circuit because of my delta side, right? And if the star neutral will be grounded through let's say some Zn, and impedance is 3Zn, which appears in the series, with Z0 in zero sequence network will be present there. The fourth one is the delta star, but this time delta is not grounded. So it is a little bit special case, you can say, because the neutral of delta is connected to the windings, right? Windings underground, right? The neutrals of delta is always connected to the windings underground. So because of that, what will happen, the value of my zero sequence impedance here will be infinity, and because of that, as the impedance is infinity, so there will be no zero sequence current which will be able to flow through my transformer windings. So that was your delta star with delta ungrounded. The fifth one is delta delta, and in this case what happens, the delta connection windings which provide no return path. So the delta connection winding will provide no return path at all, and because of that, what will happen, the zero sequence current will not be able to flow in or out of my delta delta transformer. Okay, it will only keep rotating in my deltas only. So this currents can but this current will circulate through my delta winding, so it will keep rotating in the delta winding, and such circulating currents would exist only if the zero sequence voltages are somehow included in either of the delta windings. If zero sequence voltage is included in either of the delta winding, then such circulating current would exist, but except that it will not. And because of that, the Z0 will be connected to the reference bus. As you can see here, the H and L, both of the sides are open, and Z0 is connected to the reference bus, which will be circulating zero sequence current to two deltas with and H and L will remain open. So we will wrap this lecture here. This was end of your fifth chapter, the symmetrical components. We will be starting unsymmetrical components from next lecture onwards. Till now, if you have any doubts, any queries, or any feedback related to this playlist or these lectures, please feel free to mention them in the comment section below. If you have Any suggestions related to the channel, all of them are welcome. And I will be seeing you in the next lecture. Till then, thank you very much for listening and take care of yourselves. Bye bye.